kind of a long time Rust fan, but I haven't really been using it that much. And what I want to tell you is about a project I've been working on recently that's starting to really come together, I think, in a very, very promising way. And I'm happy to present. I wasn't really sure the format, so I just put together a couple slides here that I'll go through just to give a high level, like, hey, what is the general context? And then I thought I would just like walk through a couple of things I built, maybe a little bit of code. But really, I'm just kind of hoping to meet other people who are potentially interested in looking at the code base, kicking the tires, telling me what I'm doing wrong, helping me out, etc. And I did see a few people here who are interested in graphics or low-level programming, and maybe there's some other elements that I'm directly working on or that are adjacent to some of the things I'm working on that you guys might be interested in. For example, I think that Rust is fantastic for combining the raw representation of all the protein structures in their graphical representation. So I started penciling out like a embedding plugin that would potentially allow us to seamlessly interact with the underlying data structure and represent it. So if you're at all interested in anything that I show you, the entire point of coming here to meet you, I would love to meet you, I'd love to chat. And the other thing, I don't know if anyone is here, is I've been extensively using the Hugging Face candle library, and I pinged on there a little internal Discord. So if anyone's from Hugging Face and working on that library, I'd like to meet you. So the basic background, which is this doesn't really do it justice, is proteins are awesome. So my background is I've been in biotech for 10 years. I'm a scientist. I started doing natural products in the last couple of years. I've been doing some protein design. And so it's obvious to, I think, everybody in the protein design world, but maybe a little bit less obvious about just how fast the field is moving. And so people now know about AlphaFold, or they probably already knew about AlphaFold, just got a Nobel Prize, or Dennis Thomas got a Nobel Prize. And there's a number of other companies that are also trying to apply the same sorts of machine learning tools that people are using for language to understand proteins. And so basically the premise is proteins are awesome, machine learning is awesome, and there's this flourishing field with new releases every day about how to mix these two things. But one of the nice trends is that the models are getting smaller, and so this is a figure from a recent release of the ESM2. They're trying to show that you get better results if you scale. But what's interesting is things keep coming this way, which is the models get smaller and smaller. And what I think is happening in the protein world, something that's happening also in the big large language world, which is 2 years ago you had these massive big weights that could only be run by the big tech giants, and now you have Llama 3.3 and you can run it on your desktop if you have enough RAM. And so what is interesting to me, and then this other protein MPN model, those weights are only 10 miles. You could probably run that in the ground. So the question that I was sort of muddling is, can we just make a desktop app, or can we make a web browser that will allow us to run these protein design tools without needing any big machine? Just let people iterate. And so what I'm going to talk about is this series of projects. This is a GitHub project. You can just look it up now if you have your laptop. It's just a collection of cargo, crates. And so I'm going to talk a little bit about. By the way, this is the last slide. I'm going to talk a little bit about this guy. Just show that we can use Rust to compile down, a machine learning library and run it, on you as a binary in just half a second, right on your own Mac laptop, and then just show how you could potentially package that up for distribution. So that's what I'm going to talk about, and maybe because it's easier, I'm just going to walk backwards. I'm going to show the application, briefly show this, and then we can spend a little bit of time here where maybe I think that's probably the most interesting part for this audience. So this application itself is pretty straightforward. I'm calling it. This is actually not a great example because it's already loaded. But here, this is a Tauri app. I don't know if everyone's using Tauri, but it's a Rust backend. It has an HTML front end, and this is an example web page. And when I click this sequence, submit. When I click this button, submit, it's going to take this sequence, which I just copied. It's a hemoglobin protein sequence, and it's going to load up this amplify model. It's going to run this protein through the weights, encode it, and then it's going to decode it, and it's just going to spit out. Well, actually, it doesn't spit out a sequence. Then it's going to actually calculate this contact mass. So this is if you're a machine learning person, it's the intention heads of the weights. So this is it. oh, and it, it's about a half second. So, okay, well, you get a graph, but to me this is amazing. This is amazing, right? You would have to previously, like even a year ago, just do something in the cloud, based on money and rent stuff and whatever, and now you can just do it here. So this is the 120 model. The 350 million weight takes a little longer, a couple seconds. And so I think this is awesome. This is made possible by Rust, and so now I'm going to step backwards to how this works. I did post on Twitter about this guy, protein language model. This is the actual protein language model. So this is basically taking a PyTorch model, writing the equivalent PyTorch code in a similar, somewhat equivalent, but not exactly the same Rust-based machine learning library called Candle. And then this is just a clap wrapper around that handles all of the details of the loading, the parsing, and the doing. And this is also available. So this is also basically more or less the same step, only now we're getting the compilation step, encoding, writing outputs, and so this is a little bit less interesting. In this case, I was thinking maybe I would make the output like a Parquet file so that I could look later. There's lots of little options, but this is my first attempt to say, okay, well I've got the model working, and now I can make it. And then so if we just go back now, this is I think the trickiest bit is this Ferritin project, which if you go to GitHub, if you guys want to pop by GitHub and see this Ferritin project, I have been sort of keeping a blog. You can kind of see this is like about a month so old. If you want to get into the inner details of all the problems I face, that's a good spot. And just a little bit is basically I have these series of partially implemented crates. Again, this is if you guys want to give me advice or kick the tires, this is the first like actual real Rust library that I put together. But basically, this is the core data structure that's representing proteins. These are some visualization tools that I was thinking about building, and then these are the specific machine learning models that I was implementing in Candle. And just briefly, this is kind of what it looks like. So this is kind of what Candle looks like, and honestly, I'm not really sure what's interesting, if anything, to you guys here. But basically, I started by taking the PyTorch code, throwing it into Claude, and then slowly changing each line until I could load up the PyTorch code. And it works. So that's kind of the main thing. Hopefully that's like gives a brief overview of this. I think the ability to distribute binaries, the ability to like opens up an entire world of possibility. I came in here very excited. I was like sort of brainstorming like, oh, it'd be great to have interactive, like high quality Mac app. In this case, actually, the compilation actually is a little bit tricky. I didn't get into that if you want to discuss that, but basically, almost all the libraries are written for NVIDIA CUDA, but you can cross-compile almost all of them if they're written in Rust to Mac via Metal. And it works great. It works really, really great. And so it's actually not currently possible to compile down to direct binaries for something like Linux because, and actually if anyone works on this, please come talk to me. You have the same compilation trap that you have in Python, where you have to compile for a specific combination of CUDA. You can't do the runtime. So if someone knows an easy way to compile down and use the runtime CUDA, then this could really be cross-platform. That'd be fantastic. So that's really all I wanted to talk to you about it, and I'm excited and would love to chat with you. And yeah, that's it. Any questions or comments?
Can you say just a few words about the plot that you showed us? Is it simply showing attention across what
Yes, it's simply showing attention. So the way that, in this case, the way that, one of the ways of assessing the quality of these models. So in this case, this particular model is just trained on sequence. So you have these, just like you train actually all these language models you mask specific residues, and then you say, well, which residue should I get? And so you get a series of weights, which are the probabilities of each of these positions at each of them. And then you have these various attention heads, and this is just showing the cross attention between the attention heads. And typically what you do then to assess how good the sequence model is you compare this against the structural context of known sequences. So this by itself, this is actually like a ballpark proxy for physical location, but without testing, then it doesn't really mean anything. So it's actually not very, very helpful here, but it's better than just showing a sequence. So I want to have something where you push the button, you show something. And so this actually pretty not great, right? You'd expect there to be a lot more, and actually maybe it is, because maybe the color's off. You expect there to be local structure like n+3, n+4, and some secondary structure, and then you don't see any. I mean, this is hemoglobin, so you do it folds very nicely. So this, like, yeah, if you're a structural biologist, you're like, yeah, something's wrong here. So this is the small, fastest model. I can try this again with 350. I don't have it hooked up right now, so I can't do it. But you would expect, and this is a little bit what they were showing in that graph that I briefly showed, where the sequence models get more structural information with the more parameter training. Again, it's not really my area of expertise, but what this is supposed to be doing, or supposed to be representing, is how often a residue at this position sees a residue at this position. What is the attention of the, like, how often do they